So hey everyone, this is chapter 5 of Chemical Structure and Reactivity. This is by me, and here's the shout out list. Let's get straight into it. So here's the introduction to this chapter. So this chapter, chapter 5, will now extend the study of molecular orbital theory from diatomics, which contains 2 atoms, to polyatomic molecules, which have multiple atoms. So at this point, we're just adding a whole nother level of complexity. And if we're dealing with polyatomics, we'll get to that point where we realize, hey, I just can't keep building all these pen and paper molecular orbital diagrams. It's way too messy using the current approaches that we have now. So, usually we'd use calculations to get the energies and also the forms of the molecular orbital diagrams. I will show an example of a program that I have for that, but even when we must use computer calculations, we can still use that qualitative approach of building molecular orbital diagrams. So, they still haven't fallen off, they're relevant. So, we'll start off on how symmetry can be utilized for molecules such as H3+, known as the trihydrogen cation, and water, H2O. Then, we're going to go over atomic orbitals that are hybridized, and how this can help when dealing with molecular orbitals formation of more complex molecules, especially if you're going into organic systems. So, the trihydrogen cation, denoted by H3+, is an actual important molecule for anyone that's working in interstellar chemistry. So, if you participated in WCC, the Winter Chemistry Competition held by CODS, shameless plug, and if you're in the bronze tier, which is just starting tier, you would have gotten a question about interstellar chemistry. I'm pretty sure it's your individual round. And you saw like many weird diagrams, just like overall some concepts that just like rip your current understanding of chemistry. But to someone who's working in interstellar chemistry, this is just normal stuff, especially with the trihydrogen cation, which is extremely prevalent in the environment and space. Now, these interstellar chemists use spectroscopy to analyze compounds such as the trihydrogen cation, which give off light that is later analyzed. Now, if we want to create molecular orbitals of this molecule, then we can simply view the molecule as having 3 1s orbitals, which then create 3 molecular orbitals. So, however, so far, we don't have any way to obtain how the molecular orbitals will look with current approaches, and what their energies would be. We can introduce the idea of symmetry orbitals, and how these symmetry orbitals are able to form molecular orbitals. There are 2 forms of the trihydrogen cation that you need to know, the linear form and the triangular form. Now, from experimental evidence, it's found that the trihydrogen cation is actually in the triangular form. So why are we talking about the linear form? Well, the linear form, at least in my opinion, helps to better introduce the concept of symmetry orbitals and symmetry in general. So, it's still relevant to this discussion. So, the linear form of the trihydrogen cation has many symmetry elements, but the mirror plane that passed through that central hydrogen atom is the symmetry operation that we'll consider. Now, for the 1s atomic orbitals on the first and last hydrogen atoms, we'll need to combine those in such a way to classify them as symmetric or antisymmetric. These are known as symmetry orbitals. So as you can see in the image, we have our first symmetry orbital, which is classified as symmetric. Now, this is known as symmetric because if you reflect that molecule along the mirror plane, the sign will look the exact same. So that's a symmetric symmetry orbital. And to create our symmetry orbitals, when we're talking about hydrogen atoms 1 and 3, we'll have to color code the 1s orbitals based on their sign, either positive or negative. Now, as we can see in the image, or even in my chapter 3 lecture, the slides are there, the symmetric orbital has the 1s orbitals having the same sign, while the antisymmetric orbital does not. Now, here's kind of the thing. So, you may have been fed this concept that atomic orbitals kind of have just like a region where they're just like, it's where it's just like cut off. That's not true if you think of it, because here's the thing, the only reason why they have that kind of bounded surface is to just show like where there's 90% probability density of the electrons or something. So there's still interaction between these two 1s orbitals, even if they are far apart. And using ideas of constructive and destructive interference, yeah, this would actually be supported. So, yeah, that's what makes these symmetry orbitals either symmetric or antisymmetric for linear H3+. Here's the thing. If you have these symmetry orbitals, once you create the molecular orbitals from symmetry orbitals, what you'll have to do is basically symmetrical symmetry orbitals can only interact with symmetrical symmetry orbitals. Antisymmetrical symmetry orbitals can only interact with antisymmetrical orbitals. But you can see right here, we get 3 molecular orbitals, which matches up with our observation. Now, considering that H3+, if you count the valence electrons, has 2 valence electrons, you would expect these 2 electrons to be placed in ML1, which is strongly bonding. So that's a good reason why H3+ is stable. So now we're going to extend this concept for triangular trihydrogen cations. Now, basically, this is almost like the same thing. So you have the mirror plane that cuts through a central, quote-unquote, like a hydrogen atom that lies on that mirror plane. And you also have your 2 1s orbitals that are on either end. So basically, you have your 3 symmetry orbitals. So, to create these symmetry orbitals, here's a side note, we can undergo a process known as the symmetry-adapted linear combination of atomic orbitals, known as SALC. Now, as I said, the first and second symmetry orbitals are symmetric, as they don't change signs when reflected along that mirror plane. But for the third symmetry orbital, it's antisymmetric, since the signs do change. And here's the finished molecular orbital diagram for the triangular form of the trihydrogen cation. So you can see all the concepts I've talked about into here. So it's kind of similar, honestly, to the linear form, except that the energies are different, and of course the arrangement is different. Now, there's a reason why the trihydrogen cation mainly takes on that triangular form. So, for both forms of the trihydrogen cation, we have those 2 electrons, 2 valence electrons, that are present in the lowest energy bonding molecular orbital. Now, the reason why the trihydrogen cation is more stable compared to the linear form that's because the distance of separation is less between those 1s orbitals, meaning that there's bonding character for that first bonding molecular orbital. Now, we can actually see from this graph, this is made using computer calculation. I won't get into the details because I don't know. We can see that the lowest energy is achieved. We have a bond angle of 60, indicating a triangular form. Now, what if we try just plain H3 instead? So instead of just a trihydrogen cation, it's just trihydrogen. So, we all know that hydrogen occurs at a natural diatomic form, which is H2. But what if we just try something like H3? Now, if we do something like H3, let me go back to a triangular form. So, if we have that H3, there are 3 valence electrons, which means we'll have 2 electrons in that bonding first molecular orbital, and we'll have 1 electron in that anti-bonding molecular orbital. Now, this means that the bond will thus be weaker and will have a larger bond length. So, that means that, in fact, the trihydrogen cation is more stable than just trihydrogen. Go on to more complex linear triatomics. So, we can extend the concepts taken from linear form of the trihydrogen cation, and we'll take this and go on to what's known as the bifluoride ion, which is just FHF-. So, we can construct that first symmetry orbital, which is symmetric, as it focuses on the in-phase overlap of the 1s orbital on the hydrogen atom. And because we have fluorine atoms at each end, they also have 2p orbitals. So, because these orbitals can only participate in sigma bonding with that 1s orbital with hydrogen, we use 2pz orbitals to construct our second and third symmetry orbitals. And fun fact, this ion has not been observed in the gas phase, but rather in solutions of hydrofluoric acid, for example. Now, here's some notes on the bifluoride ion. When constructing the molecular orbital diagram for the bifluoride ion, we are presented with the idea that we can just use the 2s atomic orbitals on the fluorine atoms. So, when looking at the energies of this actually, compared to the 1s orbital as present on the hydrogen atom, the energy gap between these two orbitals is way too big, meaning that there won't be any kind of equal contribution to form molecular orbitals. And compared to 2s orbitals, the 2p orbitals have a lesser energy gap, allowing for meaningful contribution. And also, for 2px and 2py orbitals that are present in the fluorine atoms, they're classified as non-bonding. Because if we consider that z-axis to be the axis that's running through the bifluoride ion, they simply cannot interact with that 1s orbital on the hydrogen, so they're non-bonding. And we'll also have to consider destructive and constructive overlap when building that MO diagram. Now, using these symmetry orbitals, we can do this finished molecular orbital diagram for the bifluoride ion. So, we have 16 valence electrons that are present. So, 14 from the two fluorine atoms, 1 from the hydrogen atom, and another one from negative charge. So, we can say that 2 electrons go into the first molecular orbital that are formed from these symmetry orbitals, 12 electrons go into the non-bonding orbitals, and that will leave a pair of electrons to go to that weakly anti-bonding second molecular orbital, which still shows that the molecule is stable. And if there's only one pair of electrons that is therefore shared across all three atoms, that means there are half bonds. So now let's go on to water. So creating the symmetry orbitals for water will be more complex because we're dealing with a bit more of an interesting molecule. So we know that a water molecule lies on the xz plane, and thus the 2py orbital on the oxygen is classified as non-bonding, which means it's just not able to participate in bonding. Or plainly, it can just be as a lone pair. So, we have to make symmetry orbitals based on the 2px and 2pz orbitals on the oxygen atom, along with the 2s orbital, which is on the next slide. And of course, the 1s orbitals that are present on the hydrogens. So we'll have to make symmetry orbitals on that too. Now, here's a construction of all symmetry orbitals for water. So, the first symmetry orbital is created from the 2s orbital on oxygen. And as we can see, we can use that mirror plane to figure out which symmetry orbitals are symmetric or antisymmetric. Using these symmetry orbitals, we can now construct our molecular orbitals, which I understand is a lot more complex, but just remember, symmetrical symmetry orbitals only interact with symmetrical symmetry orbitals, and anti-symmetrical symmetry orbitals only interact with anti-symmetrical symmetry orbitals. And non-bonding, yeah, non-bonding just does its own thing, man. This is just a small application for simple molecular orbital theory. So we can just calculate some of the molecular orbitals that are present here, and comparing that to the diagram that we have, some of them actually look pretty similar to what's shown on screen. So that's an example of water's molecular orbitals. So now we're going to move on to hybrid atomic orbitals. So I'll bring up that classic example. So methane. Methane is in a tetrahedral arrangement, and the angles of tetrahedral arrangement are 109.5 degrees. However, this absolutely does not match up with the picture of atomic orbitals that we've been fed, because all the 2p orbitals, 2px, 2py, 2pz, on the axes, they all sit at 90 degrees to each other, while the 2s orbitals is a literal sphere. So, we're just going to use a nice oversimplification, and we're going to introduce the concept of hybrid atomic orbitals, which are just combinations of s and p orbitals that will form entirely new orbitals. that have a part S and a part P character. And remember, when we form hybrid atomic orbitals, they're still on the same atom. So there are three types that you need to know: sp3, sp2, and just sp. So sp3 orbitals combine one s orbital, so just one s orbital, and three p orbitals to form four equivalent hybrid orbitals, which means that they all have the same energy. Remember that concept of degeneracy, and they all point in the same direction. And when they're all laid in their correct positions, they form a tetrahedral arrangement. And each one of these hybrid orbitals have a minor and a major lobe. And for other orbitals to have the best overlap with a hybrid atomic orbital, they must overlap with that major lobe since it's bigger. Now, this makes the hybrid atomic orbital more directional than the atomic orbitals from which it's formed. So now we're going to go on to sp2 and sp hybrid atomic orbitals. So, these sets of atomic orbitals are different because they leave room for unhybridized p orbitals. So, here's a tip based on the number of pi bonds. So, pi bonds are just created from side-to-side overlap of p orbitals. So, if there are no pi bonds, for especially like a carbon atom, then it's sp3 hybridized. If it forms one pi bond, it's sp2 hybridized. If it forms two pi bonds, then it's sp hybridized. And for arrangement, for tetrahedral arrangement, choose sp3. For trigonal planar arrangement, choose sp2. And for linear arrangement, just choose sp. Now, we're going to compare the hybrid atomic orbital approach to atomic orbital approach. So, we're going to use the example of nitrogen gas, N2, for comparing these two approaches. So, let's first assume that the nitrogen atoms in the molecule, N2, are sp hybridized, which allows for two pi bonds to be formed. Now remember, a triple bond has one sigma bond, and remember, sigma bond always comes first, and two pi bonds. So the two hybrids would form a pi bonding and anti-bonding molecular orbital since they face towards each other. And the two pairs of unhybridized 2p orbitals would then participate in pi bonding, meaning that we would then get a pair of pi bonding and anti-bonding molecular orbitals. Now, we've already covered the full atomic orbital approach to nitrogen gas back in chapter 4, so feel free to look back at that or even Google that for matter. Now, the main difference is that when we use that hybrid atomic orbital approach, we get a lack of sophistication, since of course this is a gross oversimplification, compared if we go with the full MO approach, even though the hybrid approach is still useful for some use cases. So next we're going to go on to the concept of lone pairs. So, in the molecular orbital theory world, concept of lone pairs extends from two sources: non-bonding orbitals, such as the 2py non-bonding orbital that you can find in the water molecule, and bonding and anti-bonding molecular orbitals canceling out, which creates a lone pair. So, for example, let's take out the full MO diagram of nitrogen gas, which is shown on screen. So we can see that we have a sigma bonding and anti-bonding orbital that's formed from the two s orbitals. So those cancel out, leading to a lone pair on each nitrogen atom. And in addition, we have three bonds that are formed, since we have two electrons in each bonding orbital. Now we're going to go on to even more hybrid orbitals. So we can extend the concept of hybrid atomic orbital as now, and we can use experimental data to determine the correct s character that these hybrid atomic orbitals can have. Now, sp3 orbitals take in one s orbital and three p orbitals, meaning that they have 25% s character. As for sp2, they have 33% s character, and for sp they have a 50% s character. And we can use this kind of curve to figure out the percentage of s character that's needed. So let's take example for water. The bond angle is 104.5. So we can either reduce the s character in each of the sp3 orbitals, or we can increase the s character of two of those hybrids. And one way to confirm this is to look at the PES of water, or the photoelectron spectrum of water, which I won't get into. Now we're going to end off with organic molecules. So, with organic molecules, depending on the type, there will be a difference in energy for our molecular orbitals. So, For this slide, I've shown 3 examples of molecules which we will use: an alkyl halide, an alcohol, and an amine, with all the carbons being sp3 hybridized, meaning that no pi bonds will be formed, or for that matter, pi molecular orbitals. In addition, so are all the heteroatoms that are in these molecules. So heteroatoms are just any atoms that are not hydrogen or carbon, for your information. So there are major contributors to the molecular orbitals that are formed in these systems, and the HOMO for molecules such as these, alkyl halides, alcohols, basic alcohols, and basic amines, is most likely a non-bonding lone pair that's present on the heteroatom. And the LUMO for these molecules would likely be a sigma anti-bonding orbital, though we can only be sure of this for alkyl halides, like CH3F, which is just fluoromethane. For alcohols and amines, we might have to use things such as computer calculations. Now we're going to go on to another part of organic molecules. So we're going to talk about doubly bonded and triply bonded species. So let's start off with ketones or aldehydes and imines. So we have methanol and methylene imine. So these molecules are planar in nature, meaning that they're flat, and thus have an sp2 hybridized carbon atom in the molecule. Now what pi bonds do is, how they create that plane structure is basically, if you break that pi bond relies on side-to-side overlap. If you twist it, then that pi bond will be broken. So really it just allows for that planar structure to shine through. So in terms of the molecular orbitals that are present in these molecules, the HOMO would be the oxygen's lone pair for aldehydes or ketones, or the nitrogen's lone pair for imines. And as for the LUMO, the pi anti-bonding molecular orbital is the LUMO. And for triply bonded species, the carbon atom is sp hybridized. As you can see, if we leave 2 unhybridized p orbitals, then we get 2 pi bonds, which is present in these triply bonded species. So for example, with hydrogen cyanide, the HOMO is the lone pair on the nitrogen, while the LUMO is the pi anti-bonding molecular orbital. And this can also be extended to the oxonium ion, since it's isoelectronic with hydrogen cyanide, meaning it just has the same way that electrons are arranged. Now we're going to end off with the concept of delocalized bonding, which is pretty simple. So we've mainly talked about hybrid atomic orbitals, but now we'll go back to a traditional picture of molecular orbital theory in polyatomics. So for molecules such as benzene, carboxylate ions, which are just carboxylic acids that are protonated, butadiene, and more, what we can see is that for pi electron systems, which basically arise from that side-to-side overlap of p orbitals, these pi electron systems can stretch across the entire molecule. So that shows a limitation of just the traditional hybrid atomic orbital concept. So that's just a small note there. And yeah, that's mainly the end.